Okay, so in our do now, we saw that we factored, and by factoring, we found that there are 3 zeros to this polynomial function. Today, we're going to look at polynomials on a graph, and we'll be able to count up the number of zeros, the degrees, and all of that stuff. So if you look at this first example, it asks if the degree of this function is odd or even. So just by looking at the fact that it's ending off in the same direction, that tells us that it is even. So obviously our options for a degree are any of these numbers and so on. So what we're going to do now is look at the graph, and we'll be able to count up the number of zeros and the degree of the polynomial. So sometimes the number of zeros matches the degree of the polynomial. So let's see if this is one of those cases. Number of zeros comes from, if you remember from Algebra 1, comes from when the graph crosses the x-axis. So right here would be a 0, here would be a 0, here would be a 0, and here would be a 0. So the answer to this question is there are 4 zeros to this polynomial function. Every time the graph crosses the axis, that counts as a 0. The next question says, what is the degree of the polynomial? Now, we know that it has to be even, so it's possible that 4 is the degree as well, but I'm going to show you exactly how we can find the degree based on the graph. So the degree of a polynomial is counted by tracing the graph and seeing how many times it changes direction. So that's 1. Then it starts going the other way. That's 2. Then the other way is 3. And then the last one is 4. So the answer to this is 4. So this is one of the cases where the number of zeros does match the number of degrees. Now, there are also other aspects of a polynomial graph that we're going to go over, but first I want you to look through these definitions. So the first one is what we just covered. The real zeros is where the graph crosses or touches the x-axis, and that's what we just did here. I highlighted them in green. The next 3 are brand new vocabulary words. I'm going to show you what they mean on the graph, but first I want to read through the definition. So relative maximum is the point where the function changes direction from increasing to decreasing. A minimum is the complete opposite. It's a point where the function changes direction from decreasing to increasing. And then this last one, relative extreme values, that's just all of the maximums and minimums together. So if you look at this graph, let me erase what we have on here, and we're going to talk about relative maximum and minimum. So relative minimums are, like it says, where the graph changes direction from decreasing to increasing. So it's all of those low points of the graph. Those are all called relative minimums. And the reason why they're called relative minimums is because they are the minimum lowest points on the graph. That's what minimum means. Now, the relative maximum is just the complete opposite. It's the high points of the graph. So if you think about it in terms of like if you were on a roller coaster and this was going up and down, it would be those high points right before the drop, and the relative minimums would be those low points right before it goes back up. So right here we have a relative maximum. Okay, so if I were to ask you how many relative extreme values there are, well, you would just count up all of these together. You'd count up the 2 minimums plus the 1 maximum, and it would be 3 relative extreme values. So those are your new vocabulary words. Okay, now there are some cases, like I said before, where the degree and the number of zeros do not match. These are those 2 cases, so I'm going to go through them one at a time. The first case is when there are imaginary roots. Now, I've never showed you, and you've never learned in Algebra 1, what imaginary roots look like on a graph. So remember before I said a root is everywhere the graph crosses the x-axis? Well, that is true here. These 2 are real roots. We have 2 of them. So we have 2, oops, let me write it in a pen. We have 2 real roots, or zeros, whatever you want to call them. However, if you were to count up the degrees here, we have 1, 2, 3, 4. So if we have 4 as our degree, we see here that they do not match. When they do not match, it is because we have some imaginary roots. So basically, the 2 roots that are not part of the degree would just be imaginary. And the way you can basically find out how many imaginary roots there are is if this is the degree, 4, right? We have a degree of 4. 2 of them are real. The other 2 have to be imaginary for it to come out to be equal to 4. Now, the other special case where the degree will not match the number of roots is something called a double root. So again, I'm going to count up 1, 2, oops, that's sloppy, let me redo that. 1, 2, 3, 4 was my degree, but as you can see, we only have 1, 2, and 3. I'll make it a little bit easier to see here. 3 real roots. The reason why there's only 3 real roots, it's not because there's an imaginary root, because we see that we counted up every time it touched the axis. It is because of something called a double root. And the double root is located, let me erase this, the double root is located right here. Anytime your graph does something like this, which is called a bounce, that means there's a double root there. So anytime your graph touches the axis and then bounces off of it instead of crossing right through it, that's a double root. So that is why in this case, our roots do not match the degrees. So you just need to know something very simple. If you see a double root, you count it twice, and then that would make perfect sense that there is a degree of 4. However, when you're finding the solutions, you don't have to write that number twice. That's why it's really only considered 3 real roots. But in the imaginary roots case, the reason why there was 2 roots and there was no bounce, right? There was nothing that bounced. There was nothing that should be counted twice. That's because we had 2 imaginary roots. And you'll notice, maybe by seeing it a bunch of times, you'll notice a graph that has imaginary roots, it does something like this. It has like a floating root down there where it almost comes up to the axis, but then it doesn't. That's how you know there's imaginary roots, is when it does that little turnaround direction without crossing through the axis. But either way, as long as you know how to count up the degrees, you'll be able to find the number of roots just by the process of elimination. So we'll do 1 or 2 examples together, and then we'll talk about it in the Google Meet. So this one says, what is the degree of the polynomial? So I'm going to trace it again to find out. It's 1, 2, 3, 4, and 5. And now if you look at the fact that they end in opposite directions, that makes sense, right? This is an odd graph, so 5 makes sense. 5 is odd. How many real zeros are there? Well, there are 1, 2, 3, 4 real zeros. Why aren't these the same? The next question says, why isn't 5 and 4 the same number, right? Remember in the do now I said sometimes the degree matches the number of zeros. Well, in this case it doesn't, and that's because right here it does that bounce thing. So if there's a bounce, that means we have a double root. So that root right there, that root of positive 2, we have it twice. So when you find solutions to this, if I were to give you the equation, you would get the root of 2 2 times. So that's why we only have 4 real zeros, because one of them is a double root. And the last question, is this polynomial's leading coefficient negative or positive? Just to go back to the last lesson and tie it all together, because it ends off pointing up on the right side, that means this one is positive. All right, one last example we'll do together. What is the degree of this polynomial? So again, I see that it ends off in 2 different directions, so I know it has to be an odd number. Let's count. 1, 2, 3, 4, and 5. So again, we have 5 as our degree. How many relative extreme values are there? So in order to find the relative extreme values, we're going to need to find out how many relative minimums there are and how many relative maximums there are, and just count them up. So for our minimums, we have 1 and 2. For our maximums, we have 1 and 2. So total, we have 4. How many real zeros do we have? Let me highlight that in a different color. Real zeros would be 1, 2, and 3. So that leaves us with no bouncing, so there's no double root. However, we should have had 5, so that means that the other 2 have to be imaginary, right? So 3 plus 2 equals 5.